Okay, so we're now going to begin with radicals. When you are simplifying a radical, what you are looking to do is to break it down, or factor it, I should say, into the largest perfect square and something else that's left over, unless it's actually a perfect square as it is. Unfortunately, 108 is not. These are the kinds of numbers you should be looking for. 4, 9, 16, 25. We go up to 100, but I would say it's probably more likely that it's going to be one of these values that's your perfect square, that's a factor of the number that's inside your radicand when you want to break it down. So for example, 108. That might be something that you don't really know the factors of, so if you get a little stuck with that, go to y equals, type in 108 divided by x, and then take a look at the table. Okay, you were using this before when we were factoring quadratics. You're looking for the biggest perfect square that goes into 108, so you can see right here, yes, I know that 4 goes into 108, but there's a bigger one, that 36. So now when you write this, you're generally going to want to write it so that the perfect square comes first, and then whatever the other value comes afterwards. Circle the perfect square. 36 square roots to come out to be regular 6, so that's going to go on the outside of the radical, and the thing that is not circled stays underneath the radical, and what you've now created is an equivalent form for the square root of 108 that's fully simplified. If it happens that you have variables, it's not really too much harder. The thing to remember is that variables that have even exponents are perfect squares themselves, so you really only have to worry about breaking down the 27. So 27 would factor to be 9 times 3, and obviously don't forget about that a squared. 9 is a perfect square, a squared is a perfect square. The square root of 9 is 3, that goes on the outside. The square root of a squared, when you're square rooting a variable, you chop its power in half, so the half of 2 comes out to be 1, and then anything that's not circled stays underneath that radical. When you get into adding and subtracting radicals, what's important is that you have a common radicand. So as these terms are right now, I can actually combine the 3 radical 54 and the 2 radical 54. As I combine them, I kind of want to think of them like 3x plus 2x. When you add 3x plus 2x, you never change the x. Same thing happens with these radicals. You don't change the radicand. You just combine their coefficients. So this 3 rad 54 plus 2 rad 54 becomes 5 rad 54. I'll bring down that 2 radical 6 as well. So I have to see, can I simplify this any further? Okay, so the thing is, radical 54 might break down one of our previous problems, and then maybe I can combine this a little further than I have right now. So I'm going to take that 5 radical 54 and I'm going to put it off to the side, and I'm going to factor radical 54. So again, if you get stuck, you go to your calculator, do y equals 54 divided by x. You'll find out that 54 is the same thing as 9 times 6. 9 being a perfect square means that I pull a 3 to the outside of that radical. It will get multiplied by the 5 that's already there, and the part that's not circled, the 6, will stay underneath the radical. So 15 radical 6 will be the simplified version of 5 radical 54. So now where I had 5 radical 54, I'm going to replace that with 15 radical 6. Again, they're equivalent expressions. Bring down the 2 rad 6, and now I have a common radicand, so now I can actually add those together. 15 minus 2 is 13, and remember, like I said before, you don't change the radicand. Think of it like 15x minus 2x. You're just combining the coefficients. So similar to what you just saw in the previous problem, I have radical 20 and radical 45. I don't have a common radicand, so I need to simplify it to see if I can get a common radicand. So I take that 3 rad 20 and that 4 radical 45, and I'm going to simplify them off to the side. Starting with radical 20. 20 breaks down to be 4 times 5. 4 is your perfect square. So 4 square roots to be 2 on the outside, which gets multiplied by the 3 that's already there, and then I leave a 5 underneath the radical. So that simplifies to be 6 radical 5. Put that in a little thought bubble. 6 radical 5 goes back underneath where 3 radical 20 was. Bring down that minus. 4 radical 45. 45 breaks down to be 9 times 5. Okay, I can break that 9 out to be a 3 on the outside, which gets multiplied by the 4 that's already there. And then radical 5 stays underneath that radical. 4 times 3 comes out to be 12, and 12 radical 5 is your simplified version of 4 radical 45. So I put that in place of 4 radical 45, and what do you know? I now have a common radicand, so now I can add them together. 6 take away 12 would be negative 6, and again, you keep your radicand exactly the same when you have that common radicand, so there is your simplified version of that expression. So you'll notice that with multiplying and dividing radicals, you're going to actually be applying a lot of similar things to what we did when we were multiplying and dividing polynomials. Okay, so multiplying, you're going to see that this first one basically looks like distributive property. Well, that's exactly what we're going to do here. You're going to be distributing this radical 10 to each of those terms. So I'm going to have radical 10 times radical 2 plus radical 10 times regular 2. When you are multiplying radicals, this is how it works. If there were coefficients, the coefficients will get multiplied. The things underneath the radical, they also get multiplied, but you put them back underneath the radical. You'll notice that with multiplying and dividing, I don't need a common radicand like I did with adding and subtracting. So for example, rad 10 times rad 2 would come out to be radical 20. Over here, this is a whole number 2, this is a radical 10, so I can't really combine them. I just leave that as 2 radical 10. So now I want to take radical 20, make sure that's fully simplified. Remember, 20 breaks down to be 4 times 5. That 4 comes onto the outside to be a positive 2, and then the 5 that's not circled stays underneath. So I replace radical 20 with 2 radical 5. 2 radical 10 is what's left over, and unfortunately, because these are not like radicands, this is as far simplified as that can go. If you don't have the same radicand, you cannot combine them together. So now we start getting into multiplying binomial versions of these radical expressions. And as we did with polynomials, I'm going to go back to the box method for multiplying. You're obviously welcome to use FOIL if you prefer, but I find that the box method keeps you nice and organized. I would try to set up the box so that basically the bottom right-hand corner is a little bigger than the rest, because that's where most of your simplifying is going to be if you do have to simplify. You take one of your expressions and you put it on the top, again splitting in between those terms. And then you take the other expression, put it down the left-hand side. You should know it doesn't matter which one you put on the side or on the top. You get the same answer either way. So this becomes 15, this becomes 5 radical 2, this becomes negative 3 radical 2, and then this becomes negative times positive makes negative, rad 2 times rad 2 is radical 4. Radical 4 comes out to be regular 2. You're going to add actually along both diagonals when it comes to radicals, because you're going to see you have like terms both on both diagonals, I guess you should say. So 5 radical 2 minus 3 radical 2 would be 2 radical 2. 15 minus 2 would be 13. So your final answer would be 13 plus 2 radical 2. Okay, so you're going to see an interesting thing happen in question number 3, which is actually going to be very helpful for when we get into dividing, as you can see in question number 4. Right now it looks like just 2 binomials being multiplied, so once again I will do box method. Again, try to make the bottom right-hand corner box a little bigger than the others. 2 plus rad 3 times 2 minus rad 3. 2 times 2 is 4. 2 rad 3 goes in this top box. 2 times negative rad 3 would be negative 2 rad 3. Negative times positive makes negative. Rad 3 times rad 3 is rad 9. The square root of 9 is 3. And therefore I have that simplified version in the bottom right-hand corner. As I add along my diagonals, look at what happens. 2 radical 3 minus 2 radical 3 would come up to be 0 radical 3, or just 0. 4 minus 3 comes out to be 1. So the product of these two binomials is actually just the number 1. Now where that's going to be important is that when we get into dividing radical expressions, you're going to need to use this idea of what we call conjugates. Okay, so conjugates. They are identical expressions with opposite signs in between them. Okay, so this is a plus, that becomes a minus. And what's special about them is that when I multiply conjugates together, they multiply to be a whole number. When you have to do something called rationalizing the denominator, like you can see in question number 4, you need to get it so that your denominator turns into a whole number. You don't want radicals left in the denominator, and to do that, you're going to use conjugates. So 2 minus radical 5 is the thing I want to turn into a whole number, so I'm going to multiply that by 2 plus radical 5, the conjugate of the denominator. What I do to the bottom, I'll also have to do to the top. So essentially you'll see that I'll have to do a FOIL box for the top and a FOIL box for the bottom. So just to make sure I don't make any mistakes, I'm going to label that. And I'm going to do a box method multiplication just like we did in the previous examples. So I have 1 plus rad 5 and 2 plus rad 5. And then in the bottom, that's where I have those conjugates. Remember, when you do those conjugates, you should expect to see that they multiply to be a regular whole number. Okay, so as I multiply, 2 times 1 is 2. This becomes 2 rad 5. This becomes 1 radical 5. Rad 5 times rad 5 becomes radical 25, or regular 5. 2 times 2 is 4. Negative 2 rad 5. Positive 2 rad 5. Negative and positive makes negative. Radical 25 turns into regular 5. As I add along my diagonals, 2 rad 5 plus 1 rad 5 is 3 rad 5. As I add along this diagonal, this comes out to be 7. So my numerator is 7 plus 3 rad 5. In the bottom, the 2 rad 5 and the 2 rad 5 add up to be 0. Remember, that was the whole goal of using those conjugates. 4 minus 5 is negative 1. So what I probably want to do here is separate this, so I divide negative 1 into each of these terms, and that becomes negative 7 minus 3 radical 5, and that's your final answer. That's only because of the fact that it's a negative 1. If it were like a 2, I would have just left it as 2 in the denominator there. Okay, so solving radical equations, basically the goal in all these equations is to isolate the radical, square both sides to undo the radical, and a big thing is to remember at the end to check your answers. It is very often the case that an answer gets rejected. So you're actually kind of lucky in the first example because they're already both radicals. So, and I don't have to isolate anything. I could actually go right to squaring both sides. Okay. As I do that, the left-hand side will become x plus 3. That's square root, and that square cancel each other out. On the right-hand side, I get 2x minus 4. And now I have like a basic linear equation to solve. Minus x from both sides to get all your x's to one side. Add 4 to both sides to get your numbers to the other side. 3 plus 4 is 7. And then 2x minus x is just x. So here's the thing. You have to make sure you check your answers. So I have the square root of 7 plus 3. That comes out to be 3.16. The square root of 2 times 7 minus 4 also comes out to be 3.16. That's how you know that you can keep that answer. Again, I know it takes a little bit of extra time, but there are very many times there are situations where something gets rejected. In an example like number 2, thankfully your radical is already isolated, so we can go right to squaring both sides like in the last problem, except this time it's a little different because I don't have a radical on the left. I'm going to square both sides, and as I square the left-hand side, you need to make sure you remember to FOIL that out. R minus 3 squared is really R minus 3 times R minus 3. If I FOIL that, that becomes R squared minus 6R plus 9. So my left-hand side is R squared minus 6R plus 9. On the right-hand side, the square and the square root will cancel, so I'm just left with R plus 17. And now I have to finish solving this quadratic. Minus R from both sides. Whoops. Make sure you're minusing those like terms. Minus 17 from both sides. So R squared does not have any like terms. Negative 6R minus R would be negative 7R. And then 9 minus 17 comes out to be negative 8. So now I have a quadratic equation. So as we talked about before, it's a trinomial. This is a plain old AM trinomial because there's nothing in front of R squared. So I'm going to find two factors that multiply to be negative 8 and add up to be negative 7. When you go through, you'll figure out that that's 8 and 1. They have to be opposite signs because they multiply to a negative, and the larger number has to have a negative sign. So negative 8 and positive 1. So I'm going to finish solving. R minus 8, R plus 1, set each factor equal to 0. R minus 8 equals 0 would give you R equals 8, and R plus 1 equals 0 would give you R equals negative 1. So as I said before, you have to make sure you check your answers. So if I do 8 minus 3, that comes out to be 5. The square root of 8 plus 17 also comes out to be 5, so 8 is definitely one of my solutions. On the left-hand side, negative 1 minus 3 comes out to be negative 4. The square root of negative 1 plus 17 comes out to be positive 4. This does not come out to give me two equal sides, and that's why that has to get rejected. Last but not least, question number 3. I want to get the radical by itself. So to do so, I'm going to add a to both sides. And now I have radical 2a minus 4 by itself. On the right-hand side, I'm probably going to want to write this as a minus 2. You'll see some similarities with the last question. You now have your radical isolated. So what you're going to want to do is you're going to want to square both sides to undo that radical. So as you do this on the left-hand side, 2a minus 4 will be left over. The square cancels with the square root. On the right-hand side, don't forget to FOIL this expression out. A minus 2 times a minus 2 comes out to be a squared minus 4a plus 4. So my right-hand side, a squared minus 4a plus 4. You might think that that's a small mistake, but that might end up giving you a quadratic that's not factorable, and then you're thinking about using quadratic formula and all this kind of stuff. So much easier if you make sure you don't make those little tiny mistakes. So I'm going to bring the 2a to the right-hand side, and the 4 to the right-hand side, and then I'll have a quadratic that I should be able to factor. A squared minus 6a plus 8. I'll just move this up a little. This factors using AM method because it's a plain old regular AM trinomial. So this becomes a minus 4, a minus 2, and when I set each factor equal to 0, a minus 4 equals 0 gives me 4, and a minus 2 equals 0 gives me a equals 2. So now here comes the question. Do both of those solutions work? So I'm trying a equals 4. So that's negative 4 plus the square root of 2 times 4 minus 4 comes out to be negative 2. That did work out. Now 2 is the other one. Negative 2 plus the square root of 2 times 2 minus 4 also comes out to be negative 2. So in this case, I don't need to reject a solution. But I will say very many of these problems end up with a rejected solution on the region, so make sure you always check.